Welcome to this Bactive session. Today, we are going to talk about limiting channels and different interesting uses we can give them in our vibration test. In a vibration test, we need to place one or several accelerometers to control the excitation level and one or more accelerometers to monitor the response of our DUT. Most of the controllers in the market allow you to define a response channel as limiting channel. A limiting channel is a response channel more, but if the vibration level that is measuring reaches a predefined limit that we have programmed, it takes the control of the test to avoid that the acceleration at that particular response point exceeds the limit value. Let's analyze three applications of a limiting channel: DUT protection, notching, and shaker protection. Let's imagine we want to evaluate the vibration response and find resonances of a new DUT, for example, a steering wheel prototype. We will test at a relatively low level, but we know that at the maximum acceleration on a particular part of the DUT can by no means be higher than a level, or the prototype will irreversibly get damaged. We don't expect those high levels, but the response is unknown. Therefore, we better decide to protect the DUT with a limiting channel. We will place three accelerometers close to fixing points for test control. We also install a monitor channel on the steering wheel that we will define as limit channel. In the image, we see an animation of how this channel works in a sign test. When we are sweeping up, we see the evolution of the control channels with an average control strategy in blue that gives more accurate control. Now, we establish the design limit and add the limit channel in yellow that monitors the response of the DUT at the point of interest. Approaching a frequency, the limiting channel level starts to rise up and reaches the design limit level we had programmed. At that point, it takes the control of the test to avoid that the vibration level surpass the limit, and the control level must reduce the excitation to counterbalance the extra vibration on the response. At higher frequencies, when the level returns below the limit, the control accelerometer recovers control of the test, and the limiting channel keeps on monitoring the response point. In many test cases, the response of the fixture is not flat, and some resonances appear within the testing frequency band. We must live with this, and often we try to minimize the effect of these test imperfections with a multi-channel vibration control strategy. However, there are cases where this task becomes too hard, and we cannot place the control signal within the abort band. This situation is typical in aerospace industry, where we must test big and heavy DUTs with big and heavy fixtures. In such a case, the standard allows for something called notching. It consists in a permitted reduction in the excitation level to counterbalance the extra vibration that the fixture is generating. Traditionally, the user reduces by program the reference profile within a narrow frequency band around the fixture resonance, generating a slot or notch in the reference profile. The control adapts to reduce the drive signal, and the free acceleration also reduces getting closer to the reference. Now let's see a detail of the notch. If we would use a limiting channel on the fixture DUT fixing point for this task, instead of programming a level reduction manually, the limiting channel would try to keep the level below the limit, and therefore the control excitation would be automatically adjusted. Let's see the detail. Sometimes this technique is also called advanced notching. Overturning moments is something we must always have in mind during our vibration tests due to its intrinsic risk to damage our system. Overturning moments can happen not only due to the excessive vibration in the testing axis, but also in cross-axis. Placing a limit channel, or better a triaxial accelerometer for three channels in formation, in a potentially high resonant point and far from the center of the armature will protect our shaker, not allowing the test to reach level that, multiplied by the affected mass and the distance to the testing axis, would mean an overturning moment too high for the shaker guidance system. This maximum overturning moment figure should be found in the shaker manual. In the graph below, we define the limits for both the vertical vibration and the lateral vibration measured in the triaxial accelerometer. As the test progresses, we reach a frequency band where the vertical vibration reaches the limit and the control decreases. Then, at a higher frequency, the limitation is due to the lateral excessive vibration. Summarizing, limiting channels become a very interesting option for our monitor channels in a vibration test, adding a layer of additional control to protect our DUT and our shaker from unexpected vibration that may appear during the development of the test. Want to learn more? Invest in education and sign up for our training courses. Thanks for attending, and let's meet in the next Byte Tip session.